Carbon nitride it was really graduate students and postdocs in my research group who brought my attention to carbon nitride and convinced me that this is something that we should be working on. And I would definitely say it's a collective effort. I'm happy to have just supervised a particularly productive group of people, graduate students and postdocs who all contributed, who lent their expertise and creativity and ideas along the way.
Welcome to the Project Report. Join your host, Elyse Dzenick, as she sits with researchers and highly qualified personnel working on FES-funded research. Explore what they're working on, why it matters, and what's to come.
Dr. Karthik Shankar is a researcher at the University of Alberta's Department of Electrical and Computer Engineering. Today, he's talking to me about some of his recent publications and how his research is pushing the boundaries of solar technology, but not for solar panels. He's exploring photocatalysis for water splitting, a way to store energy from the sun so that it can be used to make green hydrogen for later use. So how long have you been working on this particular research? Tell me why you're excited about it.
I have been working in the solar area for more than 20 years, but I've been working in the specific topic of using carbon nitrides as a photocatalyst and a photoelectrode since about 2015, roughly from the time that Future Energy Systems was formed.
I bet you've learned a lot since then.
Yes. And one of the things that you asked me what's exciting, and what's exciting is that carbon nitride-based photocatalysts for hydrogen generation is a field that has a lot of scientific questions to be answered, but also a lot of engineering that needs to be done. So there are a lot of topics where the focus is either purely scientific or purely engineering, but here we're grappling with both scientific issues and engineering issues.
You say the grappling with science and engineering, that's examining how certain parts of the system work, but also how the system is working all together as a whole?
Well, when we say science, we're talking more about understanding the physics of what makes these devices work, what are the optimal materials to be used so that we can get the best possible amount of hydrogen generation from a given amount of sunlight. So to increase the efficiency, so to say, of the process, all of that is more of a scientific endeavor. Whereas engineering is about scalability, thinking once you have identified the materials, how would you mass produce them most economically? How would you take care of installing them in a cold environment like in Canada? All those things that come after. So that's how at least I think of the scientific and engineering issues.
Nice.
Yeah.
That helps contextualize what you're working on a little bit more.
Yes.
Thanks. So how does this technology work?
As you mentioned, these are essentially photocatalysts and photoelectrodes. What they do is they take energy from the sun and instead of using it to generate electricity as in a solar panel, they use it to drive a chemical reaction. There are a bunch of different chemical reactions that sunlight can be used to drive, but in this case, the reaction of interest to us is the splitting of water back into H2 and O2, because water is H2O, and therefore generating hydrogen. Oxygen is more of a byproduct in this process, so the main goal is to generate hydrogen. You need to use a semiconductor because a semiconductor absorbs sunlight and generates electron-hole pairs. And now it is those electrons and holes which you use to oxidize and reduce water. The anode, you end up generating oxygen, and at the other electrode, which is the cathode, you end up generating hydrogen. But the active electrode in our case is the photoanode. So that is where we have the semiconducting material, which is in our case, carbon nitride, typically combined with a metal oxide or some other kind of scaffold. The scientific challenge consists of how to maximize the generation or creation of these electrons and holes. And then once these electrons and holes are created, how to prevent them from being lost to recombination and ensure that all of them get used to perform the specific chemical reaction that we are interested in. Because hydrogen is a gas, there's energy stored in the chemical bonds of hydrogen, which can be accessed through combustion. So you can burn the hydrogen, and when you burn hydrogen, you get steam, which is again not a toxic product, it's a non-toxic product. So in that sense, it's kind of similar to, say, burning methane, which is the most important component of natural gas. But when you burn methane, in addition to getting steam, you get a lot of carbon dioxide because of the carbon present in methane. But when you burn hydrogen, you only get water, you get steam basically. And in fact, even the industry is looking at hydrogen from that perspective. So you see, for instance, a lot of utilities attempting to blend home heating natural gas with hydrogen as like one of the first applications of hydrogen in the hydrogen economy.
Yeah, that makes sense. Thank you for explaining that.
Sure.
Awesome. And so you had mentioned carbon nitride. What
Yes.
is carbon nitride?
Carbon nitride is what is known as a two-dimensional layered semiconductor. It's also a polymer. So to understand what carbon nitride is, we'll have to go back a little bit to understanding what graphene is. So there was a lot of excitement in the early and mid 2000s regarding graphene, which is an atomically thin two-dimensional sheet of carbon atoms. So graphene is very exciting because it has remarkable electronic and mechanical properties. But graphene also has a big problem. It's not a semiconductor. It's quasi-metallic. So it doesn't really generate the electrons and holes that you need to drive a chemical reaction. But it has all the other amazing attributes of two-dimensional materials, which is that because they are like a carpet, a sheet, you are able to tailor reaction sites as you see fit on the surface. They have a very large surface to volume ratio. There are all these other advantages associated with two-dimensional material. There's very little of a diffusion limitation. So there are all these advantages. But as I said, graphene is a poor platform to access them for photoelectrochemical or photocatalytic water splitting, simply because graphene is not a semiconductor. So then comes along in about 2008, 2009, carbon nitride, which is kind of a semiconducting analog of graphene. Because so what you do is in graphene, which is what is known as an sp2 hybridized two-dimensional sheet of carbon atoms, if you take every certain number of carbon atoms and replace them with nitrogen atoms, you get a new stoichiometry, a new composition, which is known as C3N4, or graphitic carbon nitride, which is now a semiconductor. Okay, and so it has many of the advantages of graphene: this incredible thermal resistance, mechanical strength, and chemical resilience, but it is also a semiconductor. However, one problem that we identified right then is that carbon nitride absorbs mainly the ultraviolet and the blue photons in the solar spectrum, whereas the sun spectrum, extends all the way to red and even to near infrared photons, which are really not absorbed and which are wasted by traditional or what is known as conventional carbon nitride, which has a formula of GC3N4. And so one of our first attempts was to try to modify the composition to kind of narrow the band gap from 2.7 eV to 2 eV, so as to allow us to harvest a broader swath of sunlight. And then recently we have been able to push it even further, narrow the band gap almost to that ideal range of about 1.4 to 1.5 eV. So our first strategy was to increase the nitrogen amount relative to carbon, or to introduce dopants such as phosphorus. But this time what we've done is we have introduced graphene-like moieties, as they're called, or rings within carbon nitride. So we've increased the amount of carbon relative to nitrogen, so it's called carbon-rich carbon nitride, and that has allowed us, as I said, to almost achieve the ideal band gap of about 1.4 eV. And that is what has resulted in some very spectacular water splitting and hydrogen generation results, which led to being published in the Journal of American Chemical Society, and there were also a bunch of popular press articles about it.
That's really exciting to hear, and it's exciting to hear that your work has now been published and is accessible for everyone to read about and to learn about.
Yeah.
I understand that a lot of water splitting devices use critical minerals. How does carbon nitride perform differently than the critical minerals?
Elyse, I think you really hit the nail on the head. This is a very critical point that is being ignored by a lot of people. A lot of the kind of materials that are currently being considered for water splitting. So I'll give you one example: gallium nitride. Gallium nitride is a very promising material that can do many of the things carbon nitride does. However, gallium nitride has gallium, which is a relatively rare element. For instance, it's not that easy to get hold of large quantities of commercial gallium. So now you compare it to a material like carbon nitride, which is constituted of earth abundant elements. There's nothing rare about carbon and nitrogen. They're the basic ingredients of life. So carbon nitride is made of earth abundant elements, which I think should make people give it a much closer look than many other candidate prospects for water splitting, photocatalysts and photoelectrodes, because the earth abundance could be a clincher in the long run.
That's really interesting. It's awesome to hear that this composition that you're working with, carbon nitride,
Yeah.
it not only makes the device perform a little bit better, a little bit more optimized. In the long run, it sounds like it can be a lot more affordable, accessible, and also just better all around for a number of reasons.
Yes. I mean, it is also affordable for a few other reasons. The precursors that are used to make it are melamine and urea, which are used in fertilizers, which are used in laminates. These are very common industrial chemicals. So that is another advantage. And also the process that we use to make them is high temperature thermal condensation, which lends itself to scalability, unlike some other processes which are difficult to mass produce. Once the optimal composition of carbon nitride is established, it would be quite easy to make ton level quantities, not kilograms, but ton level quantities of carbon nitride.
Wow.
Yeah.
How did you go about developing carbon nitride? And then how does it apply to the device itself? Do you layer it on almost like a layer of paint?
Carbon nitride was really graduate students and postdocs in my research group who brought my attention to carbon nitride. And I would particularly like to mention a couple of individuals. Pawan Kumar, who was a postdoc when Future Energy Systems was first constituted, and he kind of got this program going in my lab. And then another individual is Narendra Chawla, who is the first author of this JAX paper that I mentioned, who had this brilliant idea. Narendra's idea was to grow the carbon nitride directly on a rutile phase titanium dioxide, and he grew them on nanowires. So we already had a nanostructure in place, and the nanostructure gives you certain advantages to optimally use electrons and holes, because it reduces the possibility of electron-hole recombination or annihilation, which would be a loss mechanism. And this is where our German collaborators helped. A couple of students in my group, Narendra, whom I mentioned, and John, basically did internships in Germany. So they went to the Technical University of Munich, where they have certain specialized equipment such as neutron scattering, and also very specialized X-ray scattering, which at that point of time were not available here at the University of Alberta. And they also have the expertise in analyzing the data. And what this collaboration demonstrated, that not only is the carbon nitride of a narrower band gap and a higher quality growing on the rutile titanium dioxide nanowires, but there is a heteroepitaxial interface which is quite rare in semiconductor physics. And that is when there is a one-to-one atomic registration between the atoms on the substrate and the atoms of whatever is being deposited on the substrate. So that is basically the most ideal form of growth, and we basically serendipitously ran into it. And that, I think, played a major role in achieving the very high performance that we saw.
What are you looking forward to, either with the research, partnerships, or just your work in general?
Yes, we are working with a couple of smaller companies who are interested in this technology and would like to take it forward. So we have some ideas to make these carbon nitrides even better. But we also hope to, at some point, attract the attention of some of the larger companies, especially in trying to apply towards hydrogen generation. Because if you think about it, it's a great opportunity for Alberta to become engaged in the hydrogen economy. And I think government officials as well as private industry are very conscious of this. At the moment, other than Russia, Alberta is the lowest cost jurisdiction for the production of hydrogen, and this is mainly because of our tremendous natural gas reserves, and there are processes that are able to convert natural gas directly to hydrogen. But what would be greener and cleaner would be splitting water to generate the hydrogen. So, the present gray hydrogen, as it's called, or blue hydrogen, which involves natural gas-based methods to generate hydrogen, is fine, because you also need an infrastructure in place to use all the hydrogen that is generated. It can't happen overnight. You can't transition from, for instance, gasoline-powered vehicles, internal combustion engines, to electric vehicles overnight. There's an infrastructure that needs, so it's the same with hydrogen. So you can't really move from fossil fuels like natural gas and petroleum directly to hydrogen overnight. There's an infrastructure that needs to be built up that allows the hydrogen to be used. And so that is now happening in the province in the context of blue and gray hydrogen, and green hydrogen will benefit from it and contribute to it in course of time.
So you mentioned that you were recently published and that a lot of your work has been picked up by a number of publications. Where can people go to find more information?
Well, the best place is the journal where the article was published. So that would be the Journal of the American Chemical Society. But also there are some science websites for science aficionados that disseminate the latest scientific advances and technologies. Our research advance was also covered in those magazine articles. Yeah.
That's very cool. Well, thank you so much for sitting down and chatting with me today.
Thank you, Elyse. And I really thank Future Energy Systems for funding all of them, for paying the bills and making all of this possible.